All right, so with all this star stuff going on, welcome to your asynchronous lesson. So hopefully you did all right on this warm-up. Let's take a look at it. So for the first one, we're just writing the equation of the circle. It gives us the center and the radius already, so really we just have to fill it in. So remember, the equation for a circle is x minus h squared plus y minus k squared equal to the radius squared. H and k is going to be our center. In this case, that is going to be at 5, 0. And our radius is equal to 6. So we plug everything in. X minus 5 squared plus y minus 0 squared equal to 6 squared. We get rid of 0 and square the 6 and get our final answer, x minus 5 squared plus y squared equal to 36. And there's our equation for the circle centered at 5, 0 with a radius of 6 units. Number 2, we're doing the same thing, but now we have our endpoints of a diameter given to us. And for this one, we need to actually do some work because the problem we did last week that dealt with this gave us two x values that were the same. So we knew that the diameter we were given was a vertical diameter. In this case, we don't have anything that's common, so it's a diagonal diameter. So we actually have to use the distance formula to find the radius, and we have to use the midpoint formula to find the midpoint. You can do that in either order. If you find the midpoint first, then use the midpoint and the distance formula with one of these 2 points to find the radius, or you can use the distance formula to find the whole diameter and divide by 2, and then you still have to find the midpoint with the center. So it's kind of up to you on whichever way you want to go with that. So for us, we're going to do the distance formula to find the length of the diameter. So that's going to be our x's, so -3, the difference of our x's, -3 minus -9, so we're adding 9, plus -7 minus 1 squared. So -3 plus 9, that's going to give us a positive 6, and -7 minus 1 is a -8. 6 squared is 36. -8 squared is 64. Add those up, you get 100. So our diameter is 10, which means our radius is equal to the diameter over 2, or 10 over 2, which is just 5 units. So we have a radius, now we need to find our center. That's going to be the midpoint between these 2 points. So -3 plus -9 divided by 2, -7 plus 1 divided by 2. Average of the x's and average of the y's. So our midpoint, -3 plus -9 is -12. -7 plus 1 is -6. So our midpoint, or the center of our circle, the -12 divided by 2 is -6, and -6 divided by 2 is -3. So we have our center, we have our radius, we're ready to go ahead and plug it into the formula. X minus h squared plus y minus k squared equal to the radius squared. And our h and k are what we just found. Since they're both negative, got to change the sign to positive inside of our parentheses for both of these. And r is 5. So the only thing now we can simplify is just to square the 5. So x plus 6 squared plus y plus 3 squared equal to 25. And that is our equation for our circle, with a diameter that has endpoints -3, -7, and -9, 1. So today we're going to take a look at the other two conic sections we haven't seen yet, ellipses and then hyperbolas. The reason we look at these together is they are fairly similar in terms of the processes to get the equations. The equations for them actually look very similar to each other. There's only one difference between them. And they include parts similar to, like a parabola had a focus, right? And some other things, but they all three of them are going to have foci. So, and ellipse and hyperbolas actually have two focuses or foci. So that's why I got to use the plural for that. So today we're going to see ellipse, foci, major axis, minor axis, center. So vertices, co-vertices, constant sum. And then for hyperbolas, we have a lot. I don't know why those all bumped up there together, but hyperbolas, you got the transverse axis, conjugate axis, foci. Again, probably didn't need that on there twice. Vertices, co-vertices, and a constant difference. So hopefully that last word there for both of these kind of guides you on the difference between the two. So an ellipse is going to have a sum in the middle, and a hyperbola is going to have a difference between the two parts. So here are the base equations for ellipses, and these are when they are centered at the origin. So you have horizontal and vertical orientations. For horizontal, the focus is at C0 or negative C0. It's both of them. The length of the major axis is 2a. Length of the minor axis is 2b. So major is the longer axis. The minor is the shorter axis. And then if it's going the other way, notice now the major is still a, right? It's still 2a. And it's still the first thing that's listed, but now on top of the a squared is the y squared because it's vertical. So our major axis is going up and down. So that means that the y is going to go first. So that's how you can tell which orientation it has based on the equation. So I'm just given the equation, and I know that the y comes first, and it's over the larger number. That means that, yeah, it's a vertical situation. If the x is first and it's over the larger one, like it's supposed to be, then it's a horizontal orientation. So the first one just gives us the ellipse on the graph, and thankfully it gives us it on the graph. So we can actually use that to our advantage to find out what A and B are, the axes for this particular ellipse. Now it gives you the focus too, but that doesn't really matter. We don't need to use that to do anything. But there's one thing that was missing off of that last slide that's kind of important, and that's how you find what C, A, and B are without having a graph given to you, or even finding what A or B are if you're given the focus, like in this case. And that equation is that C is equal to the square root of A squared minus B squared. So it's similar to Pythagorean theorem, but it's not really Pythagorean theorem. It's because the A, B, and C are in different spots, so they're not quite forming where you would think they would be for Pythagorean theorem, but they do form a right triangle. It's just not in the spots you would think. So in this case, we don't need to worry about that though, because we know it's orientated vertical, so that means that y is going to be first. It's y squared over something plus x squared over something. It's centered at the origin as well, so there's nothing being added or not equal to 1. Not being added or subtracted to the x or y. So now we just need to figure out what A is and what B is, and then square them. And since we're given the graph, we can do that with the graph. So 1, 2, 3, that's our B is 3. And 1, 2, 3, 4, 5, that's our A. So A is 5, B is 3, so A squared is 25, and B squared is 9. So y squared over 25 plus x squared over 9 equal to 1 is the equation for this particular hyperbola. Ellipse, sorry. Wrong thing. Right equation. Moving on. So now when they're not centered at the origin, it's not quite so easy because sometimes things are going to make things more complicated for us. The main thing here is that the focus changes. Now the vertices, we need to deal with those because they're not going to just be on the x or y axis this time. So we need to add a to h and subtract a from h for the vertex of a horizontal. Then co-vertices are the points that it goes out in the minor axis side. So you have to add or subtract b to k on that one. And then for the vertical, it's just the opposite. So other than that, the equations are the same. The numerators just add in a minus h and a minus k. K stays with y, h stays with x, like it always has. So this one here gives us the vertices and co-vertices. So what we need to do here, we can use the vertices to find the midpoint, and that's going to be our center. You can use either, really, vertices or co-vertices, because the midpoint to both of them is going to be the center of our ellipse. So our midpoint here is going to be negative 6 plus 4 divided by 2, and negative 2 plus negative 2 divided by 2. Now, based on the fact that my vertices have a negative 2 for both y values, that tells me that this is horizontal. It doesn't tell us that, so it's good to know what's going to go first. So x is going to be our first thing on top. So the rest of this, finding our midpoint, negative 6 plus 4 is negative 2 over 2. Negative 2 plus negative 2 is negative 4 over 2. So our midpoint, or the center of our ellipse, is at negative 1, negative 2. Now what we want to look at are the other numbers in our vertices to figure out what our a and b are going to be. So for the negative 6 going to 4, that's a gap of 10, right? It goes 6 and then it goes another 4 in the positive. So that is equal to 2 times a, which we divide by 2, and a is equal to 5. Do the same thing for the other points. We got a negative 1 for the x's. That's normal. Those should be the same. For the y, though, we have a negative 4 and a 0. So a negative 4 going to 0, that's a gap of 4. And that's going to be equal to 2b. So we divide by 2 on both sides of that one. And b equals 2. So we have our a, we have our b, we have our midpoint, our center. So we need to know what a squared is. It's 25. B squared is 4. And now we're ready to set up our equation, remembering that it's horizontal, so that means x is going to go first, with a squared underneath it. So we're going to have an x plus 1, because it's really x minus negative 1, so adding 1, over 25, plus, sorry, my class next door is being loud, and then we have y minus negative 2, and I forgot that was coming too. Sorry about the bell. Not going to re-record the rest of this. So underneath that is our 4 for b squared, and that's equal to 1. So there's our equation for the ellipse with vertices at negative 6, negative 2, and 4, negative 2, and co-vertices at negative 1, negative 4, and negative 1, 0. This next one, a listener is standing in an elliptical room, 150 feet wide, 320 feet long. So that tells us what 2a and 2b are. So remember, a is always going to be the longest one. So 2a is equal to 320. So we divide both sides by 2, and a is 160. Remember, we want to know what a squared is going to be, so we're going to square that. And that is going to give us 600. Yeah, That's it there. And then for B, 2B is going to be equal to the width of the room, 150. We divide that by 2. And B is equal to 75. We need to square that. And that is 5,625. So now we have our a squared, we have our b squared, and it says that we can say that the center is at the origin. So that's all we needed. Our center is at the origin, so our, let's see, does it say it's horizontal? So x is going to go first. So our answer is going to be x squared over a squared, which is 2,000, or 20, I did that again, 25,600, plus y squared over 5,625 equal to 1. And that's it. Thankfully for us, this one again was centered at the origin, so it made life just a tad bit easier. This next one, though, we need to actually go ahead and come up with a lot with this one. All it gives us is this equation that's not written in the format we want it in. So what we need to do is group our x's and group our y's together. Hopefully I've got enough room on the left here to do this. So we got an x squared minus 6x plus the y's. It's going to be 4y squared minus 16y. And we're going to take that 11 and put it on the other side. So we're going to add 11 to both sides, so it's equal to 11. So now we need to complete the square with both the x's and the y's. So for the x's, we have a negative 6 for our b, so we're going to divide that by 2 and square it. That's going to give us a negative 3 to square, which is 9. For the y's, we're going to get the negative, well, hold on. Before we do that, we need to move that 4 out. So let me go ahead and rewrite this a little bit here. Let me move this down for you. There we go. And we're going to rewrite this equation one more time with the 4 outside. So x squared minus 6x plus 4 times y squared minus 4y equal to 11. There we go. So we're going to have to complete the square, as I said. So x squared minus 6x plus c plus 4 times y squared minus 4y plus d, I guess. Keep forgetting about the bells being on, sorry. There'll be another one coming up here soon. Move this down again one more time. That's going to be equal to 11 plus c plus 4 times d. Because the 4 outside the parentheses and with the y's, we got to include that on the other side as well. So now we already got what c is. So there's that. We need d. That's going to be equal to a negative 4 divided by 2 squared. So that's negative 2 squared over 4. So now we're ready to go ahead and plug these numbers in. So over the x's, we have x squared minus 6x plus 9 plus 4 there's that other bell. Y squared minus 4y plus 4. And all of this is going to be equal to 11 plus 9 plus 4 times 4. So each of these large parentheses on the left side of our equal sign are perfect square trinomials. So that means we have an x minus 3 squared plus 4 times y minus 2 squared. And all of this is going to be equal to everything on the right side here. So 4 times 4 is 16. 11 plus 9 is 20. 20 plus 16 is 36. Now remember, we want this equal to 1, and we need these fractions here, right? So the last step is to divide everything by 36. So the first term divided by 36, I'm going to have to write this up on the top here, sorry, for the inconvenience of space. So we have x minus 3 squared over 36 plus 4 over 36 simplifies to 1/9. So that's going to be plus over 9. So y minus 2 squared over 9. And we divided 36 by 36 to get rid of that. So we have 1. So there is our equation up on the very top there. So our center is at 3, 2. And we know that our major axis was first, so that's the x. And now we weren't 100% sure that was going to end up that way, but because of the number underneath, the x needed to be there, so that is in the right spot. So x being first means it's horizontal, and the 36 being on the bottom means that our a value is 6, because the square root of 36 is 6. So in both to the right and to the left, we're going to go out 6. And then the square root of 9 is 3, so we're going to go up 3 and down 3 for the other point. And now we need to create our ellipse. And that's about as close as I can get to it. Now it says to find the center and focus. We're not going to worry about that because we just got this ellipse graphed anyway. And there's a whole lot of process to getting the equation in the first place. So our next thing is going to look at hyperbolas. So hyperbolas are a little bit different. They still have a focus. Instead of major and minor axes, they have a transverse axis. That's just going from remember a hyperbola basically looks like two parabolas together, right? So the transverse axis is basically just going from the vertex to the vertex. That's what that's talking about. And then the conjugate axis is something else entirely. So that's where you're going to get your A's and B's. This time, it actually does follow Pythagorean Theorem for C. So a squared plus b squared equals c squared. And we might need to use that here in a minute. So just keep that in mind. But the main difference here between an ellipse and a hyperbola is that minus sign in the middle. Otherwise, if the x goes first, then it's horizontal. If the y goes first, it's vertical. And that's it. That doesn't mean that A and B are going to be different sizes of each other. B could be larger than A, and that's fine. But they're going to stay in the same position because we have to subtract B away. So these first ones are going to be centered at the origin. So this one specifically, we need to figure out A and B. Really, we only need B to write the equation, which is what we're doing. It's already graphed for us. So A, though, is 2. Oh, not drawing ellipses right now. So A is this 2 here. And then C goes to the focus. So this is C. So C is 4, A is 2. Again, I just mentioned we can use Pythagorean Theorem to find B, but we really don't need B. Remember, the equation is, since this one is vertical, it's going to be y squared over a squared minus x squared over b squared equal to 1. We really only need b squared, so we don't have to actually square root in the process to find b. So b squared is equal to the square root of c squared minus a squared. It's just the rewritten. I didn't need to include the square root. C squared minus a squared. There we go. It's the rewritten form of Pythagorean Theorem. So b squared is going to be equal to, we just said C is 4, so 4 squared, minus A we said is 2, 2 squared. 4 squared is 16, 2 squared is 4, so B squared is 12. So we have B squared. We don't have A squared written out separately, but we did find that A squared is 4. It's 2 squared, which is 4. So now we have everything we need to plug in, and we're good to go. So y squared over A squared, we just said is 4, minus x squared over B squared, which we said is 12, equal to 1. And there's our equation. So when they give us the graph and tell us where the focus is, it's pretty simple to find. So our next one here, we are given the asymptotes for the vertical hyperbola. So we know it's vertical, which means y is going to go first. And again, it doesn't tell us that it's centered at the origin, but we haven't seen what it looks like when it's not. So this one's going to be centered at the origin. So the equation for the asymptotes, the first thing that happens with that, it's just going to be b over a times x when it's horizontal. When it's vertical like this one, it's a over b times x. And it's plus or minus that. That's why there's two different ones. One's plus, one's minus. So a over b equals 3. So we know that now. We also know that a is equal to 2 times the square root of 10 because of the vertices being there. So knowing these two things, we can plug in a. So that's going to be 2 times the square root of 10 over b equal to 3. And we can just swap these two. So it's b is equal to 2 times the square root of 10 over 3. But again, remember we want a squared and b squared. So a squared is going to be squaring the 2, so 4. And squaring the square root of 10 just leaves us with 10. So a squared is 40. For b squared, we're going to square everything. So the 2 squared is 4. The square root of 10 squared is 10. And the 3 squared is 9. So that's 40 over 9. And we're going to leave it as that fraction. That's a-okay, fine by me to do it like that. So plugging everything in, we have y squared over 40, that's our a squared, minus x squared over b squared, which we just said was 40 over 9, equal to 1. And there is our equation for that hyperbola. So now we're going to shift gears and take a look at hyperbolas when they're not centered at the origin. So the same things apply that applied to ellipses. The focus changes by plus or minus c for the h, the vertices plus or minus a, the co-vertices plus or minus b on the k. And that's if it's horizontal. If it's vertical, they just switch to the other spot. So c is added or subtracted to k, a is added or subtracted to k, and b is added or subtracted to h. And then there's the equation for the asymptotes down there, and we will be using those here in a couple moments because we do need to find them. So this first one here, we want to identify the vertices, focus, and asymptotes. So this is where we need to use those formulas. So first things first, it says to find the vertices. Those are fairly simple since we have a is 2, because the square root of 4 is 2. We have b, square root of 9 is 3. And we don't know where c is, but we can find it now that we have these two. We also know that our center is at hk, which is going to be 3, -5 here. So we need all 4 of those things in order to figure out everything we're about to find out. So first, let's find let's find our vertices, sorry. So vertices are going to be at 3 plus 2, so that's going to be our h plus a, and then k, and h minus a, k. So that's going to be h plus a, 3 plus 2 is 5, k is a negative 5. And h minus a, so 3 minus 2 is 1, and again k is negative 5. So there's our vertices. We can go ahead and plot those if we want to. 5, negative 5. And 1, negative 5. So now, based on that alone and the fact that we have x first, that tells me it's horizontal. So now we need our focus points. Again, here we're going to add what c is. We need to find c. Hold on, let's do that first. So c is equal to square root of a squared plus b squared. So the square root of 2 squared plus 3 squared, or the square root of 4 plus 9, or just the square root of 13. It's kind of ugly for these ones. So the focus is at h plus c, okay, and there's another one at h minus c, okay. So h plus c, so that's just going to be 3 plus square root 13, negative 5, and 3 minus the square root of 13, negative 5. So we're going to leave those as they are. We're not going to plot them because they're not really pretty to graph. But now we need to get the asymptotes. So this one is a bit of a process to these. So we have, I'm going to shrink some of this stuff down we've already done. That didn't work how I wanted it to. Move some things around so we have a little more space. All right. So for our asymptotes, that's going to be at y plus, well, y minus our negative 5k. So y minus k means y plus a negative 5, or sorry, y minus negative 5, so it's y plus 5, equal to plus or minus b over a, which is going to be 3 over 2, times x minus h, which is 3. So we have this plus or minus, we need to split those up. So we're going to keep the y plus 5 alone for now. We're going to distribute the 3 halves in as positive first. And 3 times negative 3 is a negative 9 halves. For the other version, where it's negative 3 halves x plus 9 over 2. Well, 5 is 10 halves, so we're going to move that over by subtracting it. So we have y equal to 3 halves x minus, so negative 9 halves minus 10 halves is a negative 19 halves. And for the other one, y equal to negative 3 halves x, so subtracting the 10 halves over now, 9 halves minus 10 halves is 1 half, a negative 1 half. So that one's a little bit easier to graph. Y-intercept is at 1 half. Slope is negative 2/3, so we're going to go down 3 to the right 2. So here's our easier diagonal asymptote to do. The other one, negative 19 halves. Is that 9 1/2? And our slope is 3/2, so positive. So here is our other asymptote. So now we don't really need to worry about finding other points, but our graph approach those asymptotes in all of these directions here, like that. And like this. So there we go. Kind of a rough process whenever you're given the equation and not a whole lot of other info, unfortunately, with these, but the main thing is getting those asymptotes because you want to make sure you're not going to cross them. So we got one more to look at. So this one's a real world application, but it's back to being centered at the origin. So the Lorentz navigation system is based on hyperbolas. Two stations send out signals at the same time. A ship notes the difference at the times in which, or at which it receives the signals. The ship is on a hyperbola with the station at the focus. We want to suppose the ship determines that the difference of its distances from two stations is 50 nautical miles. We want to write an equation for a hyperbola on which the ship lies if the stations are at negative 50, 0 and 50, 0. So what we know here is based on where the foci are, that C is going to be equal to 50. From our graph, that means that each square is 50, which means this is only 25. So A is 25. So B squared, really, we don't need to worry about B itself, is just going to be C squared minus A squared. C squared would be 50 squared. A squared is going to be 25 squared. 50 squared is 2,500. And 25 squared is 625. So B squared comes out to be 1,875. And again, in this process, we found what A squared is. So our equation, again, it's centered at the origin. Once again, this one is horizontal, so we're going to start with x. So x squared over A squared, so 625, minus y squared over 1,875, or B squared, is equal to 1. And there is the equation for this one. And your exit ticket is the next slide on the Nearpod. Sorry for the length of the video, guys. It is what it is. Can't really do much with it for right now, unfortunately. And I'll see you guys on Friday.